Welcome to class. Today we're going to talk about power series solutions around singular points. So it turns out working with singular points can still be possible, provided they are at least regular. What does that mean? It means that if the term from which that, or if each term in my ODE is still differentiable when I multiply it by x minus x naught to the k. In other words, my power series solution plugs the holes in the non-differentiability of my coefficient functions. So let's take a look at an example of how we would even determine that with this problem here. So you'll notice this is not in standard form. That's the first place we'll start. Dividing over the x squared minus 9, I get that y double prime plus, this guy factors, I'm going to leave it as 5 times x plus 3 over x squared minus 9, because that'll show off something in just a second. Y prime minus 12 over x squared minus 9, y equals 0. And you'll notice I can simplify this function here by canceling the common factors of plus 3, x plus 3, excuse me. And I get 5 over x minus 3, y prime, minus 12 over x squared minus 9, y equals 0. And hopefully we can see here that plus or minus 3 are singular points, since my coefficient functions become undefined there. Here, you'll see it's not defined at 3, and this one is not defined at plus or minus 3. So we need to do a little bit more investigation. How would we determine if they are regular or not? By looking at this piece. So here, in my first degree term, I'm going to look at the first degree power series term. That's the x minus 3, right? So let me specify over here. I'm looking at the root positive 3 first. So I'm going to take that root and multiply it by the first degree term. So I get 5 over x minus 3. That just gets me 5, which is certainly differentiable. In fact, everywhere, but at the singular point is where I care about at least. But remember my naming convention's a little bit backwards. This guy is P1, this guy is P2. Right? So when I move on to P2, I need to multiply by the second term, even though that's the 0th order derivative. And notice what I'm left with this time is 5 over x plus 3, but that's still good to go at positive 3. So what this tells me is that x equals 3 is regular. I'd encourage you to pause the video here and check to see if you can show that negative 3 is in fact irregular. Frobenius' theorem, which, no shade, but that is one of the most egghead names out there, I think. Frobenius' theorem says that we still actually have at least one power series solution centered at regular singular points. The only weird piece about it is that, first of all, its power will certainly be skewed, and second of all, it only converges in one direction, or in other words, its radius of convergence only extends to one side of the singular point. So let's take a look at the repercussions of that in our problem-solving strategies we've developed so far. I want to look at this function, this ODE, 2xy double prime minus y plus 2y equals 0, and I want to find a general solution on 0 to infinity. And previously, that would have immediately become a problem, because when I write this guy in standard form, I get that y double prime minus 1 over 2x y plus 2 over 2x is 1 over x y equals 0. Oops, y prime, missed my primes there, equals 0. And we see x equals 0 is singular. It's singing, I guess. And with our previous methods, well, we just kind of can't use them. We don't have a regular power series solution. Instead, well, I guess we should say we do have a regular power series solution because we need to adapt our problem-solving method just a little bit. You may be wondering, why am I bothering trying to center around 0? Because I need 0 to be in my interval. I need 0 to be in my interval of existence or convergence for my power series. All right, let me clean up the board so we can get started. Okay, we verified that 0 is in fact a regular singular point, so we do still have hope. That hope comes from Frobenius' theorem, which tells us the explicit form of that power series solution. It looks like we just shift our power by some number r, where that number is yet to be determined. But here's the general form. So why don't we try the normal, and by normal I mean ordinary, power series solution method of taking the derivatives, plugging it into the differential equation, and seeing what we get. Let's start with those derivatives. For those derivatives, I just use the power rule, and now plugging into the equation, I end up with these three terms on the left-hand side of my ODE. Next, you'll notice that these r's floating around in the powers are kind of making things difficult, except that, using my properties of exponents, I notice I have a common factor among every term in every sum of x to the r. In the first one, for example, I can factor out x to the r, and I'm left over with an x to the k minus 1. Repeating this throughout the rest of these terms, here's what I get. Here's what I get. Now I know that certainly there is no r value I could choose to make the left-hand side 0, and x is the variable for a general solution. It's not going to identically be 0. In other words, this factor of x to the r isn't relevant to finding the general solution. So we get to just kind of ignore this factor and look at the stuff in the parentheses. This almost looks like a regular power series scenario, except that I've still got r's floating around, albeit not in the powers anymore. So next up, let's combine all of these power series into a single term by getting them in phase with each other. I notice here I start counting from x to the negative 1 when I plug in 0, x to the negative 1 when I plug in 0, and x to the 0 when I plug in 0. To make sure I start from the same power of x, I'm going to shift both of my first two power series up by 1 by stripping out the first term. Here's what that looks like. And then last but not least, I just need to refactor these. I'm going to let n equal k minus 1 in both of my first two terms, and just to make it match, I'll switch that third term over to n. That will let me combine all three of the power series. I'm going to clean up the board and write it down. Here's what I get when I refactor and combine like terms. You'll notice that I have organized this guy to write it a little more neatly. Here's all the coefficients that I get once I factor out my x to the n's and combine all my like terms. Remember, that allows us to develop a recurrence relation for our coefficients. I know that because the left-hand side should equal 0, it must be that on every different power of x, its coefficient ends up being 0. So this line should equal 0 for all n. Solving for Cn plus 1, I get the following recurrence relation. There we go. Now, you'll notice immediately that if I just had C0, I would be done, because then I'd have all my other coefficients. Well, except for the fact we haven't determined what r should be either. But luckily, there's one last piece of information we haven't used yet, and that's this guy, the terms that we stripped out. If that coefficient equals 0, then I actually have three cases to consider. It could be the case that C0 is 0, but do you notice if C0 is 0, what's C1? It's 0. So what's C2? It's 0. So what's C3? I think you get the point. Taking C0 to be 0 gives me the trivial solution. So sure, I did find a solution, just not an interesting one. Now, Frobenius' theorem only guarantees me at least one. It doesn't tell me how many r's I would expect to find. These two, however, are sufficiently different. It wouldn't be very interesting if I got r is 0 and r is 1, for example, because that's just the power series shifted up one more term. So really, I'm looking for, in this problem, two different power series, which means I need two r values that don't differ by an integer. Here, because these differ by 3/2, which is a rational number, not an integer, we're good to go. So these two values of r are what are going to give us our two distinct solutions to the ODE. But I've run out of room, so let's recap. So to totally recap, we used the indicial equation, as some books refer to it, this guy, our coefficient that had r's in it, to determine what the possible indices, or r values, are. We use those indices to develop unique solutions, or linearly independent solutions, I should say. That said, here's two fundamental solutions for the ODE. If I plug in r equals 0 throughout, using my recurrence relation for the coefficients here, I get this power series, the first few terms of which are 1, 2x, negative 2x squared, 4/9 x cubed, and so on. Plugging in r equals 3/2 into the exact same equation gives me a linearly independent power series solution. X to the 3/2 minus 2/5 x to the 5/2 plus 2/35 x to the 7/2, and so on. And you'll notice that they're linearly independent because no powers of x match. In fact, as long as my indices don't differ by an integer, meaning I can't count until I get to the next index, that's going to be true. So using these two fundamental solutions, I can derive the general solution as having the form c1 y1x plus c2 y2x, where ultimately those two different parameters come from the initial condition, the initial coefficient we couldn't determine in each power series.